What is D-Wave's adiabatic quantum computer? Imagine a computer that solves complex puzzles by gently guiding a quantum system to its lowest energy state. That's what D-Wave's adiabatic quantum computer does. It's a special kind of quantum device designed to handle tough optimization problems. Instead of traditional computers crunching through possibilities one by one, this machine uses a process called quantum annealing. It starts with qubits, which are tiny quantum bits, in a superposition of many states. Then, it slowly changes the system's energy landscape, encouraging the qubits to settle into the lowest energy configuration. This final state reveals the best solution to the problem at hand. The core idea behind this machine is the Adiabatic theorem. It says if you change a quantum system slowly enough, it stays in its lowest energy state. D-Wave's system begins with simple conditions and gradually morphs into a complex problem encoded in the qubits. As the system evolves, quantum tunneling helps it escape local minima, or small dips in energy, to find the true lowest point. This process is especially useful for solving problems, where finding the absolute minimum is tricky for classical computers. D-Wave's hardware is built with superconducting qubits made from niobium loops. These loops contain Josephson junctions, which are tiny barriers that allow quantum tunneling. The qubits generate magnetic fields that interact through couplers, creating connections similar to entanglement. By adjusting the magnetic biases and coupler strengths, the system maps the problem onto the physical qubits. Once the annealing process ends, the magnetic fields are measured, and the qubits' states tell us the solution. This approach, called quantum annealing, is a practical version of adiabatic quantum computing. It's less precise but faster and more robust against environmental noise. It exploits quantum tunneling to jump over energy barriers, often outperforming classical algorithms like simulated annealing in solving complex optimization tasks. Over time, D-Wave's machines have grown from about 1,000 qubits to systems with thousands of qubits, allowing them to handle more complicated problems. Most problems tackled by D-Wave are mapped onto an Ising model, which uses spins that can be either plus or minus 1. The goal is to find the configuration that minimizes the energy function. To do this, users translate their problem into this form and embed it onto the hardware's qubit network. Applications include logistics, machine learning, material science, and finance, where finding the best solution quickly can save time and money. D-Wave systems also let users customize the annealing schedule, which can improve performance for specific problems. This flexibility helps researchers and engineers experiment with different approaches to see what works best. In essence, D-Wave's adiabatic quantum computer is a tool that uses quantum physics principles to solve real-world problems faster than some traditional methods. It's a step toward harnessing emerging quantum technologies for practical, impactful solutions.